Okay, so in this video, we're going to continue our derivation of the TD, tetrahedral character table. Very exciting character table here. And in the last video, part one, what we figured out is that there's 5 classes. The 24 symmetry operations could be grouped into 5 classes, or ought to be grouped into 5 classes. The identity, which is always in a class by itself. The principal rotation axis, which is the C3, and there's 8 of those, because there's 4 C3s and 4 C3 twices. C2s, there's 3 of those. There's 6 S4s. Well, 3 of them were S4s, and the other 3 were S4 3 times. And then 6 mirror planes, which we call sigma Ds. And our first character table rule tells us that the number of classes in the symmetry operation has to equal to the number of irreducible representations. So we have 5 classes. So we're going to have 5 irreducible representations. Another word for that is 5 vectors. So we're going to have a 5 by 5 matrix. We're in 5-dimensional symmetry space here. And we don't know what these vectors are yet, so we can't assign them Mulliken symbols. So for now, just as placeholders, we're going to call them gamma 1, gamma 2, gamma 3, gamma 4, gamma 5. Very first one on every single character table derivation video that we do, we always put ones across the board first. Every character table has a totally symmetric irreducible representation. So that's a freebie. We're 20% of the way there, 1/5 there. The next part that we always do is we figure out these values, which are the dimensionalities, or this first column. And the way we do that is we know another character table rule states that the sum of the squares of this first column, or the dimensionality as we call it, is equal to the number of symmetry operations in the point group, also called the order of the point group, which in this case is 24. I just summed up these coefficients in front of the classes in case we forgot, how many, that there were 24 symmetry operations. And we know that these dimensionalities have to be 1s, 2s, 3s, 4s, or 5s. Usually they're only going to be 1s and 2s, unless you have a highly symmetric point group, then you're going to have maybe 3, 4, or 5. Well, tetrahedral is one of those highly symmetric point groups, so you are going to have a 3. And you can kind of walk through this, and since you only can have 1, 2s, or 3s, or 4s, or 5s, you can't have a 5, because 5 square is going to take you to 25. That's already beyond 24. You can't have a 4 because that would take you to 16. And then what? If you just play with this, let's say so this was 16, 4 squared, and then this is already forced to be a 1. If these were all 1s, that'd be too low, right? That would get me to 20. If one of them was a 2, that would get me to 5, 6, 7, 23. It's still too low. And then the next one would be 8, 9, 10, 26. That doesn't work. If instead I tried one of them to be a 3, you just try some guessing here, that would get us a 9, right? 3 squared is 9, 10, 17, 18, and then there's no number here. That gets you 6. Square root of 6 isn't an integer, so you're no good there. So that tells you can't have a 4. So there's no 4s, so it would have to be 1, 2, or 3s. You just have to play with numbers here in order to do this derivation. And so let's try a 3, that'll get us 9. Let's try this another 3, that'll get us 18, 19, and then we can maybe see that we're 5 away, and a 1 and a 2 would get us there, right? And so that's sort of the way to do this, right? So 1 squared plus 1 squared plus 1 squared equals 24. A lot of times this is very easy to see because it's only 1s and 2s. Here is a little trickier because we did have some 3s. But now we have another part of our character table puzzled out. We have this first column, and that's going to help us quite a bit. From here, how we've solved most of the character tables thus far is we've tested different functions. And I've always liked to start out with z. We can try that. So we can try the z function. And so we can put that down somewhere, let's say here, and see how z is transformed. What I can tell you is that these are pretty hard to visualize, and the math gets pretty crazy for a lot of these because the tetrahedral geometry works in 3 dimensions. That's in fact why you have these 3s here. But we're going to actually be able to do it at least for x, y, and z functions. And we're probably going to stop there and then puzzle out the rest using other strategies like orthogonality. So here we go. Let's try to do this. So we have x, y, and z. We set up our Cartesian coordinate system just like we always do. And the way that we're going to do this is we are going to think about the methane molecule there, right? So let's think about that methane molecule, CH coming out, okay, towards us. That's the x-axis here, and then we have that's how I want to define this, is going kind of it's not going to be along the x-axis because the x-axis is actually going to be here, but I want to define the z-axis this way. Okay, now remember this angle here in a tetrahedron, right? We know the bond angle of methane is 109.5 degrees about. Okay, we'll get into that in a bit. It's actually the arc cosine of -1/3, which gets you 109.47 something degrees. Okay, we chemists usually just call it 109.5 degrees. But it comes from geometry where that is of the tetrahedron. But so x and z are forming, this is a right angle right here. So that's a right angle. So this is actually coming down a little bit. But I want that x axis to be near there. Okay, and I want the z-axis to be going along this CH. This is just how I'm defining it. You could define it other ways. Your y-axis is going to be coming out, and then you'll have the other parts of your molecule, right? So something like this. Okay, so at this point, what we can do is think about the first operation. Well, how do we usually do this, right? We say, hey, identity is the first operation in the identity class, the only operation in the identity class. What does that do to z? It takes z to z. Okay, that's not very interesting. What does a C3, okay, do to z? And so at this point, that actually, if we define our z, is our principal rotation axis, right? And our C3, one of our C3s goes through here. We have 8 C3s, but we only have to pick one symmetry operation from that class because mathematically they're all the same. So we're choosing the one that is coincident with the z. Now, if you have a z pointing up, we've done this many times in other videos, and you're rotating it at 120 degrees, it's still going to be pointing up. So z goes to z. What about a C2? And this is where things start falling apart a little bit and it gets a lot more complicated. The C2 here is, if you remember from the previous video, and I'm going to go back to the slides, the C2 is bisecting this angle, okay, formed by the z-axis and not the x-axis, is bisecting the angle from the z-axis and the other CH bond. So it's bisecting the 109.5 degree angle, right? That's what this is doing. And so this gets, a little, we have to do some trigonometry here. And so I'm going to rewrite this axis in a different way. But again, this C2 is bisecting here. We're doing 180 degrees. And so I'm going to write this now just in 2 dimensions here, not thinking about the y, but just the x and the z, just to help us visualize this, okay, because it's hard to draw in 3 dimensions. And we know that this CH bond is coming down here. So this is one of our CH bonds, and this is the other CH bond, right? Okay, C is down here, but you get the idea. This is C and H is the way you can draw it if you want instead. And we know this angle is 109.5. And mathematically, I'm not going to show you here, but where this comes from is actually a pretty simple geometric derivation, which is just the arc cotangent, or the cosine inverse of -1/3. And that equals in degrees 109.47 degrees. That's where you get that 109.5 degrees that you always learn in basic chemistry about the angle of a tetrahedron. Okay, so now that we know that that's just going to help us put some trigonometry to this value. So theta is here, and we're bisecting it. That's what the C2 is doing. The C2 is bisecting. Okay, and so what we are essentially doing now is we're asking, how is the Z rotating, right? The Z is going to reflect, if we have a Z vector, the Z, here's Z, this is what we're asking, what does the C2 do? We're rotating, there's our C2, 180 degrees. And so this Z is going to spin 180 degrees, and it's going to end up popping out somewhere based off of this angle. It's going to rotate actually this angle amount, okay? And what is this angle? This angle here, well, it's half of this. So if we draw this as theta, let's call it alpha, maybe. Alpha is going to be equal to 1/2 cosine inverse of -1/3. Okay, basically just the inverse of that. So we're doing we're doing half of that because of bisection. We're doing a rotation, right? And an easy way to visualize this, just with a simpler example as an aside to help you visualize, is let's say we just had X and Z, and we did a perfect bisection here. 45-degree angle, right? In that case, we know that if we're doing a 180 degrees, and this was a 45, okay, and that's a 45, therefore, that X and Z would interconvert. Another way of saying that is X got rotated 90 degrees and this way, and Z got rotated 90 degrees this way. So by exact analogy here, Z is getting rotated by 2 alpha down to here somewhere, down to some linear combination of X and Z. And that's a rotation function. And many times in these derivations, we have thought about rotation functions. And I'm going to, we usually say cosine theta. We've usually been talking about rotation along a Z. So we've been doing cosine theta is whatever this 2x2 matrix. Sine theta, usually we do a negative sine theta here and sine theta. And then whether or not there's a negative sign here just depends on whether or not you're going clockwise or counterclockwise. That's not too important, it turns out, for the math here. But, or sometimes we do it this way, right? For x, y. And so now we are rotating, actually, that's usually when we're rotating along the z. Here, we're rotating effectively along not a z, but we're rotating along effectively a y, right? Because our x and z's are spinning. So when we rotate along a z, x, we got something in terms of x and y. When we rotate along y, we'll get something in terms of x and z. And so this is going to actually turn into a z here. And the component that we really care about in this case is thinking about, what happens to z. And so you can see z is going to go into some linear combination, negative sine theta x times cosine theta z. Okay. Now, in the end, so what this is already telling us is that x and z are transforming together. Okay. And what we can also see here is that what I want to tell you right now, actually, is that if you look ahead, and you look at something like, let's do sigma d. The sigma d, the C2s are coincident with the sigma d's, and that's why I brought this up in the first video. But here's a view of it. And so you can see that the C2 and the sigma d's go together. So there's one of the sigma d's, which we could use when we get to this point, is going to be there. But what that's going to do is, in this picture, right, the y-axis is coming out towards us because this is a flat picture. And so if the sigma, one of the sigma d's is in the xz plane, y is going to also be transformed. Okay. And so and x and z aren't. And so, and furthermore, if you look at something like an S4, in the S4 case, that's going to be a sigma h that's horizontal to this. Okay, and so very difficult to visualize, but whatever this rotation that you're going to be doing is, then is going to get flipped. That's going to have some y component. So it's a long way of saying that x, y, and z vectors are all transforming with one another. We're going to have some linear combination of x, y, and z for most of these cases. One case is enough, right? As long as we find one of these cases, x, y, and z transformed together, all across the whole vector, we have to treat them as a 3x3 matrix. And so we're going to put this as x, y, and z transformed together. That's what we kind of rationalized out here. So we're now going to have, right, for identity, we're going to have an x, y, z vector. That's going to be identity matrix, right? And that's going to be, remember, the trace of the matrix, which gives us 1 plus 1 plus 1. We signaled the trace or the character of the matrix, where the word character comes from, as 1 plus 1 plus 1. We use this chi, it just means character or trace of. The identity operation equals 1 plus 1 plus 1, the sum across the main diagonals, which is equal to 3. I realize you're going to have to look at some of the other character derivation videos to understand where this is all coming from. This is one of the more complicated cases, but that's why we have a value of 3 here. Okay, and so we're going to revisit the C2 one, but the C2 one helped us begin to realize that x, y, and z all transform together. Let's go back and now do the C3, because the C3 is actually simpler. Okay, but now we know that we actually have this 3x3 matrix we have to think about. And we know z went to z. And so that's going to look like this. But we know that for x and y, I'm not going to write out what they are because it's some trig functions. But x and y have to be using this with except x and y there. Okay. Because why is that? Because the C3, one of the C3s that we defined that we like to think about was coincident with the z-axis. And so we're spinning that bottom of the tripod here. And I think we should probably draw this a little differently. Let's draw this like this to help us see this better. But there's the bottom of the tripod, there's the top, and now we're spinning this way. And this atom's going to that atom, this atom's going to that atom, this atom's going to that atom. We're doing a 120-degree rotation. So that's a simple 120-degree rotation where x goes into some linear combination. We have this formula where this is xy now. And so we just write that down. So that's going to be cosine 2 pi over 3. We're doing a pi over 3 rotation. And we need to be rotating by 2. We're doing a 2 pi over 3 rotation. Sorry, we're doing 120 degrees. That's 2 pi over 3. So cosine 2 pi over n, where n equals 3 because of C3. So that's cosine 2 pi over 3. I'm not even going to worry too much about these, but this is going to be 0, 0, and this is going to be a minus sine 2 pi over 3. This is an off diagonal component, and this is sine 2 pi over 3. Sorry for small writing, but these are off diagonal elements. The ones that matter are the on diagonal ones, so that gets you that the trace of the matrix, the character of the matrix, is cosine 2 pi over 3 plus cosine 2 pi over 3 plus 1. That is negative cosine 2 pi over 3 is negative 1/2. You remember your unit circle, so that's negative 1/2 plus negative 1/2 plus 1, that gives you a 0. And so your character here that we derived now is 0. So we're making progress here. Now we can go back to the C2 case. Now we're ready to do this. And so really now what we can see is that, again, we need this x, y, z. And so what we were considering was the z case here. And for the z case, you know, I was saying that it's this cosine theta thing. And we figured out from before that when we had a 45-degree, right, and we did a 180-degree rotation, that interconverted x and z. And the reason why it did that is because there's 2 times of 45 degrees, which is a 90-degree rotation. So x went to z, z went to x. Z went this way, x, okay? And so what is z going to do? It's doing a 2 alpha. It was the degree rotation, okay? And so what is 2 alpha? 2 alpha is, well, alpha is 1/2 cosine inverse of negative 1/3. So that means 2 alpha is cosine inverse negative 1/3. Okay? Well, if that's true, then what is z transforming in? Z is transforming to negative sine 2 alpha x plus cosine 2 alpha z. And all we care about is the on-diagonal components of this. So the on-diagonal component is whatever the function goes into itself. So you remember the matrix multiplication. So the on-diagonal component is this cosine. So what we're going to have, our on-diagonal component is cosine of cosine inverse negative 1/3, which is equal to 1/3, because these cosine inverse of themselves cancel, right? Negative 1/3, sorry. So this on-diagonal component is negative 1/3. I don't even have to worry about the off-diagonal components. All right, so that is part of it. Now the x, okay? And so what is the x value here? Well, if we know this is alpha, and it's 1/2, the x component here is there's a right angle here, right, between x and z. So this angle here that x is getting rotated by is 90 minus alpha. But we know from this logic down here that we have to take that times 2. So we have to do, so if we call this like phi, let's say, so we're rotating by 2 phi. So let's figure out what phi is. Phi is 90, alpha was 1/2 cosine inverse of negative 1/3. And what does 2 phi, that's what we're rotating by, well, that's 180 degrees minus cosine inverse of negative 1/3. And what are we figuring out here? Again, it's the on-diagonal component. The on-diagonal component here is saying, hey, x is going to go to cosine theta, whatever we're rotating by, plus cosine theta x plus sine theta z. We don't care about the sine theta z part. We just care about the on-diagonal part, which is the cosine theta x. So we have cosine of this, of 2 phis, what we're rotating by, cosine minus 180, cosine inverse negative 1/3. And this actually equals to, anytime you have cosine, there's just a trig relationship here. So cosine pi, or 180 minus x, let's just call it cosine 180, sorry, switching to radians there for a second. Cosine 180 minus x is actually just equal to minus cosine x. Okay, you can prove that. That's one of those trig identities. You know, there's all these different trig identities that are very useful. And that's one of them. So anyway, this ends up just being negative cosine of cosine inverse of negative 1/3. Well, the cosine of the cosine inverse of negative 1/3 is negative 1/3, and the negative of that is just positive 1/3. So you end up for the x component of having 1/3. And now the beauty of this is that this C2 is, I sort of said how it's this rotation along the y. And if we do if you think about the way to think about this, it's hard to visualize doing a 180-degree rotation, I think, we're now asking what happens to the y vector, okay? And so the way to think about this is, I like to think about it is, the answer, by the way, is the y vector goes to negative y. And so this becomes a negative 1. But why is that? If you do a rotation 180 degrees along the x, okay, that is going to definitely, I think you can see you're spinning it this way, right? So you're taking the y and you're spinning it, okay? Taking the y and you're spinning it behind. So it's going to go to the negative itself. If you similarly do it 180 degrees that way, you're taking the y and you're spinning it that way. Still goes the negative itself. And so if you do any off-axis, anything in the xz plane, it's still going to spin it that way. It's just spinning it 180 degrees, still the negative itself, it's just off-axis, okay? And so that's going to be a negative 1. And so then, at this point, we're done figuring out this character pretty much. We just take the trace of this, right? And the trace of this, or the character of it, is just 1/3 plus negative 1 plus negative 1/3, and that equals negative 1. And so now we can say that we have a negative 1 here. Okay, so that was definitely a very hard one to visualize. And, you know, from here, what I'd like to do is skip the S4. The S4 is even harder because now you're doing a C4. And so this x is going to go into combination of x, y, and z. So we can't use the tricks that we did with the C2 with being 180 degrees, unfortunately. And those are pretty hard tricks, right? Still has some pretty nasty math. So we're just going to skip this one. And we're going to use principles of orthogonality to help us figure out what it must be. But what we can do is we can rationalize sigma d pretty easily. And so let's do sigma d. Sigma d, again, we're going to have x, y, and z. And we saw that the sigma d, right, was how we defined this was in the xz plane, one of these sigma d's. And so what that means is that x is going to go to x, right? Z is going to go to z if it's in the xz plane. And y is going to go to negative y because the plane of the mirror is right here, right? And y is looking at itself in the plane. It's in front of the plane, so it's going to go to the minus of the plane. So that matrix is very easy to figure out. X went to x, so we put a 1. Y went to negative y, so we put a negative 1. Sorry about that straight line. And z was in the plane, so we got a 1. We take, so that gave us x, negative y, and z, right? That's the transformations we're doing. We take the trace of this matrix, and we get, so chi of sigma d is equal to what? 1 plus negative 1 plus 1. That is equal to positive 1. So we can know the character is 1. And now we can back out what this S4 can be using the principle of orthogonality, since we did most of this. And so that's going to be fairly simple. Let me just quickly make a little bit of room here so that we can write this. But basically, I can say it in words first. We know that one of the character table rules is the great orthogonality theorem, which is that all the vectors must be orthogonal to one another. And so what that means in math terms is that their dot products must be equal to 0, right? They're perpendicular to one another. And so based on that, what we can say is that gamma 1 dot product with gamma 5, which is what we're figuring out right now, has to be equal to 0. And so that's a very easy way we can figure out this last term. But this dot product is a special dot product. It's a dot product that takes into account the number of symmetry operations in each class. And so let's go through this. Basically what this is going to be is, well, gamma 1 is a 1. And then I'm going to multiply by gamma 5 term, which is a 3. And then I'm going to multiply by 1. That's the number of symmetry operations in the class. That's what I was talking about with adjusting for the number of symmetry operations in the class. And then it's a sum. Dot product is a sum, right? There's gamma 1 is 1. Gamma 5 term is 0 here, and there's 8 symmetry operations in the C3 class. And then we have the next one. Gamma 1 is 1. We have a negative 1. And there's 3 symmetry operations in the C2 class. Then we have gamma 1 being 1. This is x. We don't know what it is. We're trying to figure it out. But there's 6 operations there. Okay, and then we have a 1, and a 6. And that all must equal 0. And so we add this up, got 3 plus 0 is 3, minus 3 is 0. And so then we're ended up with just 6x plus 6 equals 0. I think very quickly you can figure out that that means x must be equal to -1. So we forced it to be orthogonal, and that saved us a lot of complicated visualization and trigonometry, figuring out that last character. All right, so that's a good stopping point. And what we're going to do in the next video is we're going to figure out what to do next to get these last 3 remaining irreducible representations.